Our next speaker of the morning is Sean Lowry from Drury University, who will talk to us about implications of blockchain consensus mechanisms.
Thank you. Like you said, my name is Sean Lowry, and I'm going to talk about the implications of blockchain consensus mechanisms. Here we go. So just to give you an overview of what I'm going to talk about first, I'm going to need to give you a lot of background. And I don't expect you to be familiar with any of these things, but I'm going to try and explain them the best I can because they're important if we're going to understand consensus mechanisms, which is what I'm going to be focusing on. And the two consensus mechanisms in particular are proof of work and proof of stake. And I'll get into those in detail, but those are the two most prominent, and they're the ones that everyone's buzzing about. So, and once we have those laid out, I'm going to try and draw some conclusions on them about what they tell us about just blockchain in general, cryptocurrency, the community at this point in time. So let's begin. Starting with the Byzantine generals problem. This problem is important if we're going to understand the motivation behind blockchain technology. So bear with me for just a minute. Let's pretend we have a castle and it is surrounded by the Byzantine army. And they're split up into these 5 camps, and each camp has its own general. So we have a distributed system here. So if all of these generals attack at the same time, let's say dawn on the next day, then they will surely win and win the castle, no problem. But if they attack at separate times, or if they only have a portion of their forces like this, they will lose. So the question becomes, how do we establish a full agreement between these distributed parties about the time to attack, and how do we, more importantly, how can they trust one another? So for a long time, this problem was just unanswered because let's say they could send messengers to one another, but if the messengers get intercepted, you need to make sure the messenger got his message delivered. So you'd probably have to send a messenger back. But how can you trust that that messenger wasn't intercepted and replaced with like a traitor? How can you trust the generals that they're not traitors, that they're actually going to do what they say they do? So this is the problem. And it's even worse in a computer system, because if the distributed nodes in a computer system do not have consensus, then it will result in just a catastrophic failure and nothing will work. So that, with that in mind, that brings us to blockchain. I'm going to talk about blockchain just in the most general terms at first, and slowly add some layers to this, because I think it is a little difficult to understand, and there's just a lot of moving parts to it. So in its most simplest form, it is a distributed database. People will often call it a distributed ledger, but I'm looking at blockchain not from the perspective of transactions just yet, although that is what it's been mostly used for up to this point with cryptocurrency. And so let's look at it here. We have a blockchain is just a chain of blocks. Blocks is what we store our information in. When you want to add a new block to the chain, let's say we want to add this one, it's append only. So you only add to the I guess the top of the chain, however you want to look at it. And we put our data in here, whatever data we want to keep. We have a header which stores important information about the block, such as like a timestamp. And we'll get into more detail of this in just a second. And then the header is used to connect this block with the rest of the chain once everything has been validated on the network. This keeps the blockchain immutable. You can't go back and change elements of a blockchain because it's already been connected. And to go back would mean having to like almost rework the whole blockchain to get to that point. So it just can't be done unless you have an enormous amount of computing power. And we'll talk about that. It's transparent, meaning anyone can pull this up, download it, and look at it. And that's kind of the beauty of it. It's available to anyone, but they can't mess with it. Moving on. That brings us to Bitcoin. It's a peer-to-peer electronic cash system. This was the title of a white paper by Satoshi Nakamoto, which he released in 2009. Satoshi Nakamoto is not a real person. It's a pseudonym for a person or a group of people that released Bitcoin. They had this pseudonym for a reason, because they wanted to get Bitcoin off the ground and then distance themselves from it, because they wanted it to be decentralized, meaning no central authority. And so, for example, in the Genesis block, Satoshi Nakamoto left a little note, and the Genesis block is the first block in the blockchain. It has to be kind of like hard coded in because it has nothing to reference before it, right? And he just said, it was the newspaper headline for that day. It says, Chancellor on brink of second bailout for banks. This was after the 2008 financial crisis. So people had lost faith in some of their banks, and that's kind of where Bitcoin came in. It wanted to get rid of the middleman. And this is where we get Satoshi protocol, which I'm going to explain more, but this is used to secure the blockchain. Okay, so here's our blockchain, and here's our network of nodes. These are all the people on the blockchain. They have these crypto wallets which they can use, and this uses the blockchain to verify that these transactions are legitimate. So you can't like double spend, that kind of thing. You've probably heard of miners before. They are a type of node on the network that verifies transactions, and they do that to earn rewards from the system. So we have unverified transactions going to the miners. They will create candidate blocks, put the verified transactions in there, and then they will compete with one another to add it to the blockchain. And whoever wins this little competition gets the reward for that block in the form of subsidy, which is the newly minted Bitcoin and the transaction fees that they verified. So the consensus mechanism is this part in red right here. It's the actual competition and the process of verifying the transaction, making everything secure. And we're going to dive into that a little deeper because that's what we're concerned with. So I think it's important for us to talk about the block header for a second. This is actually a block header from a simulation that we made. So I'm going to try and break down kind of the parts of this block header here. As you can see, there are these really big hashes here. We have these hexadecimal hashes. Satoshi Nakamoto really liked hashing. So these are all throughout the blockchain. Let me see here. These are cryptographic hash functions, okay? So it's like an SHA 256 hashing algorithm. These are like the same kind of thing that you would use to encrypt a password and store it in a database so people can't see the plain text password. The Merkle root up here is just all the transactions hashed together until they're one single root that we can use in the header. I'm not going to talk about transactions as much. The hash of the previous block, that is when we take the entire header, hash the contents, and we have this hash. So you put the hash of the previous block in this block header, so you actually connect the blocks. That's how the blocks are connected. I'll talk about the nonce a little more on the next slide, but it's important to mention the difficulty. The difficulty is how the miners know when someone has mined the block. And in this case, the difficulty is very, very low. The difficulty is basically the number of leading zeros in this hash. So you can see in these two hashes here, there's only 1 0. That means you could just randomly make hashes and you would probably get a hash with a leading 0 1 in 16 times because it's hexadecimal, right? So that's a really low difficulty, of course, but it's just a simulation. So moving on now to the actual mining. We have this pool of miners here. Miners can mine in a pool or solo, but it's more common to mine in a pool because you probably make more money that way. They take transactions, they put them in their candidate blocks. So they have to verify all these transactions first, put them in the block, and then they hash the whole header once everything is ready. And that hash is compared to the difficulty. If it's lower than the difficulty, then they have mined the block basically. And if it's not, then they have to iterate the nonce and try it again. And this process is mining, just hashing, checking, iterating over and over and over. And they will do this with, well, I'll get into that in a minute. But let's say they have found the correct difficulty, or the golden hash, as they say. Then that block is broadcast to the rest of the network so everyone can see it. The rest of the blockchain, I should say, the nodes in the network will validate that block, make sure it is legit. They will make a Coinbase transaction and it will be added to that block. And that includes the subsidy and the transaction fees going back to the miner who mined the block. And then finally, it can be added to the chain and the creation of the next block can take place. So that is the mining process. And this process of hashing over and over and over as quickly as you can is mining, basically. And its proof of work is the consensus mechanism is called proof of work. I just explained how that consensus mechanism works. It uses computational power as the scarce resource. That's kind of how Bitcoin gets its value almost. And the more miners you add to the network, the higher the difficulty goes, because the difficulty is dynamic. It will adjust to the point where the blockchain will release a block almost every 10 minutes. That's how it works. And this has led to what is a computational arms race. You can see in this graph here, over time, the hash rate across the entire network has just exploded because they no longer use their CPU or even their GPU to do these hashes. They have specialized machines called ASICs to do it. And they get thrown in these warehouses just by the millions. And it's very inefficient, very just a kind of a waste of energy, in my opinion. And that brings us to proof of stake, which is kind of the focus of this talk. It was introduced by Peercoin in 2012, kind of just basically as a replacement for proof of work, because proof of work is very computationally expensive, maybe not sustainable for the long term due to how much the Bitcoin network has grown. Miners are called minters in this case. They stake their assets in order to participate in validation. We add the coin age, which is basically just using time as our scarce resource instead of computational power. So this means much less hashing, because one unspent transaction output, or one coin day basically, is equal to one hash attempt. So instead of a quintillion hashes every second like we see in the Bitcoin network, it would be almost nothing compared to that. And for the environmental impact, first I'll talk about proof of work. It has, I've been following this, and it has the energy consumption about on par with the country of Thailand, which I don't know if that helps you understand this any, but it's kind of interesting. You in order to participate in mining and actually makes decent profit off of it, you're going to need, at this point, a full warehouse of these ASIC machines. I forget what ASIC stands for. Anyways, and this has also just created a lot of e-waste with this computational arms race. The outdated equipment just gets thrown away and it goes to landfills. It has led to a global shortage of superconductors. That's why it's really hard to get GPUs right now. I will say one good thing about proof of work though, and it has led to the growth and adoption of renewable energies, because a lot of these miners, they want the cheapest form of electricity, right? Because they want to, reduce their overhead. Proof of stake, almost no computational cost, and you can run it on a Raspberry Pi. That's how the protocol works. It's just that much more efficient. And I won't spend too much time on this because I know I'm running out of time, but here I'm just showing the efficiency based off Bitcoin, Peercoin, Ethereum. Decentralization and governance, proof of work is more decentralized. And a 51% attack just means someone would have to get control of 51% of the entire network's computing power in order to like hack it, basically. It's where they can double spend. But on the governance side of things, they have no governance because it is so decentralized. So that is a problem when it comes to updating the blockchain. Proof of stake, higher chance of centralization because you have this idea of the rich are able to stake more. And so the rich get richer, so it's not perfect. It has its flaws. But this leads to on-chain governance because one stake is equal to one vote. So they can actually update their blockchains. Skip. So significance, what's the takeaway from all this? Well, Ethereum is moving to proof of stake. That's that's kind of a big deal in the community. El Salvador just released a Bitcoin law where they have moved over to Bitcoin as like the official currency. And I think it caused Bitcoin to like crash like by 11% or something. NFTs, I'm not even going to talk about them. I think they're kind of dumb. But what I'm trying to say is there are other applications of Bitcoin, other applications of blockchain besides cryptocurrency. And the main idea I have here is just that consensus mechanisms represent a much larger debate within the blockchain community. That is, what should the trade-off be between decentralization and efficiency / sustainability? You have Bitcoin, which has superior decentralization, but they're kind of behind the game on efficiency, sustainability. And then you have new blockchains like Ethereum, which are pushing ahead to try and pick up the slack. And it's going to be interesting to see how it pans out in the future. That's my talk. Thank you for listening.
Thank you, Sean.
Thanks.